Hi guys, Mr. Rocco again. We're going to pick up with the intro to topographic maps. In the first video, I did some of these first parts here. I'm going to jump right now into principles of contour lines. I might, like I said, skip through a few things. Again, it's interactive, so but I'll go through as much of it as I feel we need to cover. So let me get right into principles of contour lines.
Principles of contour lines. Topography means the shape of the land. A topographic map shows to scale the width, length, and variable height of the land above or below a reference plane, generally mean sea level. Showing the shapes of landforms is what makes a topographic map useful.
Sea level is always going to be 0 feet, 0 meters.
A contour line is a line drawn on a topographic map that connects all points that have equal elevations. The reference plane from which elevations for contour lines are measured is called the datum, usually means sea level. The datum used for determining elevations on a topographic map is usually indicated in the lower central margin of the map. On the map illustrated, the National Geodetic Vertical Datum of 1929 refers to the mean sea level as of 1929. To illustrate the concept of contour lines, imagine an island whose highest point is 55 feet above sea level. We'll raise the sea level by 50 feet and draw a line on the corresponding topographic map that marks the shoreline of the island at each 10-foot rise of the sea.
So this is actually a lab that I would do. I don't think I'm going to be able to do it this year with COVID, but basically the students get this clear plastic looking shoebox looking thing, and I put a volcano inside of it. It's a plastic volcano, and then what they do is fill the box with water 1 centimeter at a time, as you see kind of what they did here. Each time they then put a lid on top of the box, and they look directly over top of the shoreline of the volcano, and they trace the shoreline to show the different elevations. And that's kind of what the same thing this animation does.
The result is a contour map showing the elevation and configuration of the island before sea level began to rise.
So you can see the first line out here is sea level, that's 0. And then as they filled the box or the island with water, they were going every 10 feet. So there's 10 feet, 20 feet, 30 feet, 40 feet, 50 feet. Again, that's what a topographic map shows. Just think top view. The first 3 letters of the word topographic spell top. So you're looking down, a top view down onto Earth using lines to show elevation, contour lines.
Contour lines conform to certain guidelines. Some of the general rules are: 1. Every point on a contour line is the same elevation. For example, this entire line is at exactly 5,100 feet.
Right, so these are very important rules. You might want to go back and play this section over again. So every point on this line is exactly 5,100 feet. And then the next line would be a different elevation, each one.
2. Contour lines never cross one another or divide.
That was the rule we had last week. I gave you that assignment drawing isotherms, isolines, which means they can't touch, they can't cross.
3. Widely spread contour lines mean gentle slopes.
So if you see the lines spread out like this is the topographic map on the bottom, and this is kind of the 3D model. So when the lines are spread apart, that means it's a gentle slope. Spaced apart lines or widely spread out lines, gentle slope. And then the opposite is true.
4. Closely spaced contour lines mean steep slopes.
Right, so you can see here you have a steep, almost kind of like a cliff. but it's a very steep slope, and notice the contour lines are very packed together to indicate a steep slope.
5. Hills are shown with concentric, closed contours.
So when you have a, circle in a circle in a circle, it doesn't have to be a perfect circle or oval. Anything where you have these closed contour lines, one inside the next, that indicates a mountain or a hill.
6. A contour line forms a V pointing upstream when crossing a river or stream.
So that's an extremely important rule. So if you can see down in this picture here, you've got a blue line to show a river, and then these contour lines all make a V shape when they cross the river. The V's point uphill or upstream. So this river would be flowing, they'll ask that question, and I put it on some assignments this week. It'll say, what direction is the river flowing? When they say direction, they want a compass direction: north, south, east, west, northeast, southeast, etc. So you got to give a compass check. Don't say up and don't say down. You want to use a compass direction. So in this case, these V's are pointing generally north, maybe even a slightly northeast. So that means the river's flowing opposite the V's. The V's point upstream. This river would be flowing south or southwest.
7. Closed depressions on the land are shown with closed contours with hachures that point downslope.
So if you remember, way over here in the bottom right corner was a hill with these closed depression or closed contour lines. What they do to show a depression, it's called, or a crater going down slope, they add these little tiny short lines. Notice how they point. You start at the line and you draw a little short line in each one. That's to show not uphill but downhill. So they call those depression contour lines, to show a downslope if you're going into a crater.
Notice that contour lines repeat on opposite sides of a closed depression.
So you can see if you were walking up this hill and then you get to the top, there's a little depression, sort of like a volcano kind of situation. This line's 280 feet, 290 feet, then you have 300, then you go up over the rim, it's called the rim, and you come back down, and this first depression line is always going to be the same elevation as the last solid line on the outside of the rim. So they repeat. So it's 280, 290, 300, then you go up over, and this is 300. So it's almost like if you had a person standing on the inside of the crater and someone on the outside of the crater, and they dug a hole, you could make a tunnel, they'd be at the same elevation. Then if you have another depression line, as you see you do, then you drop down, in this case 10 feet. So you got repeating on this side, then it goes down, then you come out on the other side because this is symmetrical, and so it's back to 300, up over this little rim, and then you're still at 300. So again, it repeats on either side, and then it starts to go downhill, 290, 280, etc. In this case, and the next one will show you it repeats on one side, but the other side, the land is just going to keep going uphill so it doesn't repeat. And land does what land does. It doesn't do only one thing.
Except when the closed depression is on a slope, where the contour lines will repeat on the downslope side, but not on the upslope side.
Right, so you can see in this case, on the left side of this crater, it repeated, just like in the last example. It went 280, 290, 300, up over this little rim, back down to 300, 290, but then when you come out on the right side of the crater, it didn't go back downhill, it kept going up a hill, and so it didn't repeat on this side. So again, you got to be very careful when you read topographic maps. Can be tricky, can be a little tricky.
The change in elevation between any two different adjacent contour lines is the contour interval. The contour interval of a USGS topographic map is usually indicated in the lower central margin of the map.
So the contour interval is the difference in elevation between each consecutive line. So like basically, what are you counting by? Like in that last example, they were counting every 10 feet. Maps are going to use nice easy numbers. They're going to count by 10s. They might count by 20s, 50s, 100. They're not going to count by 3s. They're not going to count by 7s. They're not going to count by 21s. They're going to keep it nice, easy. 10s, 20s, 50s, 100s. They're going to use nice, simple, round numbers.
Contour lines are drawn at multiples of the contour interval. For example, for a contour interval of 10 feet, the lines may read 5,110 feet, 5,120 feet, 5,130 feet, etc.
Right, and that's if you're counting with a contour interval of 10. Official topographic maps, the ones made by the USGS, United States Geological Survey, they put the contour interval at the bottom margin of the map. It's always at the bottom.
To help determine the elevations of contour lines, on most USGS topographic maps, every fifth contour line, called an index contour, is printed as a bold line with the elevation indicated.
So they're not going to put numbers on every line. Every fifth line, they're going to make it a darker brown line. They're going to bold it. So like, I don't know if you can see on this map. This one here is called 5,050. Then they're going to give you 4 lighter brown lines and then another bold line, every fifth one. So this one says 5,100. Be careful when they ask for the contour interval, because a lot of times what students say is they'll take this number, 5,100, and they'll subtract 50/50 and say, oh, the contour interval is 50 feet if you subtract 5,100 minus 5,050. But you got to remember the 4 lines in between. So one way you could do that is you could subtract the index contour lines, these two, and then divide by 5, right? Because 4 lines give you 5 spaces. 1, 2, 3, 4, 5. So if you said, all right, 5,100 minus 50/50, that's 50, but then do 50 divided by 5, that's 10. The other way you could do it is trial and error. I tell kids just try to count by 10s, count by 20s, see what works. So if I know this is 5,050, then I go 5,060, 5,070, 5,080, 5,090, 5,100, which I can see that is. If it didn't come out to the number written on the next bold line, then you got to change your interval you're using. Maybe it's not counting by 10s, maybe it's counting by 5s, maybe it's counting by 20s, and you just kind of trial and error there.
Also, reference points of elevation, called benchmarks, are often shown on the map and can be used to determine elevations.
So they will give you these exact known elevations. They will put a letter X, or sometimes they'll put X and the letters BM, which stand for a benchmark. And then that's an exact elevation. So this one up here in the top right tells you that right at that spot on the Earth, it's exactly 5,132 feet. And then you got another benchmark over here in the bottom left, 5,081 feet. Benchmarks are these metal, they're made out of brass or aluminum, and it's kind of like a rivet, and they stamp them into the ground. Usually you see them either at the bottom of a hill or the top of a hill on a mountain. But they're put out there by the USGS to let you know some reference points. They're not going to put them everywhere, but they're reference points.
What is the highest contour line elevation of the land shown on the area represented by this topographic map? Click on the most appropriate answer.
So what we would do is look at the map. You can see this bolt, this is that index line, 5,450. This one's 5,500. So again, try 10s. If this is 5,450, this would be 5,460, 5,470, 5,480, 5,490, 5,500. So that works. So our contour interval is 10 feet. Well, if this is 5,500, then the next line in would be 5,510. Right? So you click on that and then see if that's right. And it is.
What is the lowest contour line elevation of the land shown on the area represented by this topographic map?
So now we're looking up here in the top right. You see those are called those depression contours. So they have those little, they're called hachures, H-A-C-H-U-R-E-S. That shows downslope. So that shows a crater. Again, the general rule is this first line, this first depression line, you have 2 of them. See, 1, 2, is the same elevation as this solid line, the last solid line. But in this case, you're just going straight downhill. You're not at the peak. So it repeats when you get to like the top of a volcano. That's different. In this case, we're going to go down slope. So if this is 5,450, let's say this is 5,440, 5,430, 5,420, 5,410, 5,400, this would be 5,390. So let's try that. Oh, it's not. 5380. Okay. Oh, sorry. That's what I did wrong. Mr. Rocco messed up. So this was 50. I was doing this line. So this is 5400. I said the lowest. My bad. So this is 5400. This is 5390. This one is 5380. Right. So I was doing the first depression line. My bad. Moving on.
In addition to indicating elevations, contour lines can be used to determine the directions in which rivers and streams flow.
Right, so again, as we talked about earlier, the contour lines make V shapes. So you see, here's a river here. These contour lines make that V when they cross. When they cross a river, they make a V. The V's point upstream or uphill. Rivers don't flow uphill, right? They flow downstream. So in this case, this river right here is flowing, you could call that east, maybe even slightly southeast, east-southeast. This one over here, again, notice the V's. The V's are pointing toward the southwest, so this river's flowing toward the northeast. Opposite way the V's are going. Opposite the V's.
Click the map icon below to refer to the electronic topographic map. Locate Salt Creek, west of the St. Charles Reservoirs. Study the contour lines that cross the creek.
We'll just skip this part.
Toward what direction? Using contour lines. Contour lines have many uses. Among the most important are A. Determining the elevation of points or places, B. Measuring the relief of the land, and C. Calculating the slope of the land. As you have seen, a contour line connects all points of the same elevation on the surface of the land. Therefore, determining the elevation of a point or place involves reading the contour line if the point is on the line, or estimating the elevation of the point using the contour interval if the point falls between contour lines. This diagram illustrates a contour map and a perspective view of the same area. Choosing from the answers provided below, indicate the contour interval used for this map by dragging the correct answer to the box provided.
Okay, so let's see. So you're looking at, if you can see way over here on the left, this bold index line, contour line, is 100 feet. Then you have 1, 2, 3, 4, and then 200 feet. So you could try tens. 100, this is 110, 120, 130, 140, 150, doesn't work. Then go to 20. This is 100, so 120, 140, 160, 180, 200. That works. So I'm counting by 20s, so I'm just going to drag this 20 over here. And click, is this right? And it is.
Now, indicate the correct elevation for points A, B, C, and D by dragging the correct answer to the boxes provided.
So you're going to see this on some of the assignments this week. So we'll start with A. A is sitting right on a contour line. So again, this was 100, and our interval is down here, 20 feet. So that's 120, 140, 160, right? Because you're going uphill. So we're going to put a 160 right there. Then you see I have 200. This is 220, 240, 260. Now notice where the letter B is, or the X that represents B. It's halfway between. So again, use your best judgment. If this is 220 and this is 240 and this is 260, you're in between 240 and 260. So it's got to be something greater than 240 but less than 260. So that's going to be my 250. We'll put that there. C is on a line, but now we're heading downhill because we're going toward the water. So again, this is 100, so we're going to take 20 away each time. So this would be 80, and then minus another 20 would be 60. So C should be 60. Drag that there. Then we're going uphill. So this is 100, this would be 120, this would be 140, and this is 160. So D is between 140 and 160. So we're going to go with 150. And then we're going to check these and make sure Mr. Rocco didn't mess up. And I didn't.
Relief is defined as the difference in elevation between 2 points. Total relief is the difference between the highest and lowest points on the map. Example: highest point, 5,344 feet. Lowest point, 4,780 feet. 5,344 minus 4,780 equals 564 feet total relief.
So you just subtract the highest and lowest numbers. That's total relief. Or you could do local relief. They'll give you 2 points on the map.
Local relief is the difference in elevation between 2 specified points. What is the local relief between the top of Mount San Carlos and the benchmark in the northwest corner of this map? Drag the correct answer into the box.
So we have a benchmark up here in the northwest corner. It says 5,132 feet. We have this benchmark over here, the top of Mount San Carlos, 5,344 feet. So if we subtract those numbers, right, and get rid of the 5,000, just do the hundreds place and the tenths and the ones. So it'll be 3 minus 1 is 2, 4 minus 3 is 1, and 4 minus 2 is 2. So 212, 212. Let's see. Put that in there. Yep.
Slope is the change in elevation between 2 places divided by the horizontal distance between the places. Slope equals change in elevation divided by horizontal distance, usually expressed in feet per mile or meters per kilometer.
So this is also called gradient, which is on the front of your ESRT. So you do the change in elevation, and then you divide that by the distance. Again, it's going to be feet per mile or meters per kilometer. And we'll do a couple examples here quick.
Examine the slopes indicated with lines on both the model and accompanying contour map of an area in south-central Colorado. Notice the fact that contour lines that are close together indicate steeper slopes.
Right, so you can see on the left-hand side, these contour lines are spread out, right, over here. So that's why it's not as steep. And then if you look on the right-hand side, notice the contour lines are a little more packed together. That's why it's a steeper slope or steeper gradient.
To determine slope A, subtract the lowest point from the highest and divide by the horizontal distance between the points. Change in elevation, 5,150 feet minus 5,090 feet equals 60 feet. Slope equals 60 feet divided by 1/2 mile equals 120 feet per mile.
Right, just remember when you divide by a half, that's like doubling the numerator, the top. So double 60, that's how they got the 120. So they're going to ask us, I think, to do the other slope over here, slope B.
What is the slope along slope B? Type the answer in the box below.
So we have 5,340 feet minus 5,230 feet. That's 110, right? Yes. And then 110 divided by a half, which means double 110, which would be 220. So let's type 220 and see if we're right. Yes, we are.
Topographic profiles.
I'm going to go back and skip this part. And let's see, drawing a contour map.
Drawing a contour map. Drawing a contour map using points of known elevation involves the following steps. Examine the points of elevation and choose a suitable contour interval. Keep in mind that the smaller the contour interval, the more detailed the map will be. On the map illustrated, we will use a contour interval of 10 feet.
So this is similar to what you had to do on that assignment with the isotherms, except they're going to get harder as we go here, but we'll be doing more practice with these.
Beginning with the lowest elevations, draw the appropriate contour line, estimating the elevation between those points that do not fall directly on the contour line. Label the contour line with its elevation. Using the selected contour interval, proceed to successively higher elevations, drawing and labeling the appropriate contour lines. As you draw the contour lines, keep in mind that higher elevations will always be found on one side of the line and lower elevations on the other side.
Right, so you just want to think sequence, right? This is 20. Notice on this side, they left the 17, and then greater than 20 is in here. Less than, it has to be anything in between 20 and 30, right? Anything between the 30 and the 40 has to be in the 30s. Anything in here has to be 40s, 50s, etc. Again, the tool you want to use on these is pencil. Will they ask you to draw all these lines on a Regents? Nah. What they'll ask you to do, a lot of times, I'm trying to think what they do. They would have a bunch of these done. They might have the 20, the 30, the 40, the 50 done, like half the map. And they would ask you to pick up where they left off and draw the 60, 70, 80, 90. So a lot of times that's what they'll do. They'll draw the first four on this specific map, let's say, and then you might have to draw the second set of four. So they'll give you like a good head start. So I wouldn't say worry about drawing all of them. They don't really ask you to do that. Or sometimes what they'll do is they might draw the 20, the 30, the 40, even the 50, let's say, and then they might say only draw the 60. You might not have to draw the 70, the 80, the 90. So I always caution students, read the directions carefully. They might only tell you draw one line, the 60. But a student will start looking at these and say, oh, contour lines or iso lines, whatever. And they start drawing all of them, the 60, the 70, 80, 90. But you were only asked to draw, let's say, the 60. In that case, and that comes up, if you draw more than the directions ask you to, then the extra lines you draw have to be all correct in order to get the point. So you basically wasted your time drawing all the lines just to get the same value by drawing one. You're going to get 1 point whether you draw the 60 or you went ahead and just drew extra lines for no reason. So I always tell kids, be very careful. Read those directions very carefully. Very carefully.
Click and drag the mouse on the map to plot the 20-foot contour line. Use the Start Over button to clear your line and try again. Check your contour with the How's This button. Click Next Contour to draw another contour.
So this is kind of interactive. They want us to draw the 20, but it doesn't really draw it. I'm just kind of moving the mouse in this general area. And if I click How's This, I don't know if it's really keeping track of where I'm putting the mouse. Let's try the 30. So if I went 30s here and a 30 here, and then click How's This? Oh, I guess it didn't do it. No. Anyway, we'll skip this part.
Click and drag the mouse. Click and aerial photographs and satellite images.
All right, I'm going to skip that part. Okay, so that's it for the second video. Profiles are looking at taking a top view, turning it into a side view. I'm going to hold off on that for this week. I'll probably cover that next week. That takes a little bit more involvement, and it's not hard, but I want to go over that in a separate video. So I think that's it for this video. What I'll do is I'm going to make one more video for the week, just summarizing a lot of the stuff that this computer program talked about when it comes to topographic maps. So I'm going to make one more video, and then there'll be a bunch of assignments to do as usual for the week. Okay, talk to you soon, guys. Hope all is well. Bye.